Welcome all of you. In the last couple of classes, I discussed fundamental concepts of NMR spectroscopy, starting from spin of the nucleus, and then how do you arrive at the nuclear spin by an empirical rule, and what are the nuclei which gives rise to NMR, and then we discussed about interaction of the nuclear spins with the external magnetic field, which we call as Zeeman effect, and then degeneracy of the transitions in the presence of the magnetic field will be removed, degeneracy of the energy states, and we calculate the energy between these two, and the energy difference between these two we calculated for a particular frequency which we observed to come in the radio frequency region, and we arrived at the resonant condition nu is equal to gamma into B naught over 2 pi. Same thing conceptually we understood by classical phenomena, considering the nuclear spins, ensemble of nuclear spins. In the absence of the magnetic field, they were all randomly distributed. Once you put it in a magnetic field, there is a preferred alignment of the nuclear spins in the direction of the field or in the direction opposite to the magnetic field. According to Boltzmann rule, we also understood that more spins are there in the direction of the magnetic field than opposing it. And then we worked out what is the population difference for different magnetic fields, and we found out it is very small. We said NMR is highly insensitive, and also we observed not only what are the factors which are responsible for this sensitivity of the NMR signal, which is magnetic field, gamma, temperature, etc. We found out at low temperature good sensitivity becomes better and better. When the temperature is infinite, the spins, both energy state spins become equal, that is called a saturation. During saturation we do not get any signal, and we also understood about how do we get the signal by applying a radio frequency pulse, by perturbing it, by inducing transitions, and we understood what is a random phase approximation. We introduced the concept of bulk magnetization. Bulk magnetization is stationary and it is in the direction of the magnetic field. To detect NMR signal, we have to perturb it by applying a radio frequency pulse in a direction perpendicular to it. Then we collect the signal as a function of time. This signal is called free induction decay. We do the Fourier transformation of it and we get the NMR spectrum. And we also understood what is the line width of this thing, what is the width of the peak by uncertainty principle, and also what are the selection rules for observing the transition in different coupled energy spin system for one single spin, coupled 2 spin, 3 spins, etc. we understood. And all these selection rules also we know from all these examples there should be change in the magnetic quantum number between two energy states is either +1 or -1. These are all allowed transitions, that is a selection rule. Anything other than this are forbidden transitions. So everything we discussed, and now we will go further. Today we are going to discuss about what is called internal interaction parameters which are responsible for NMR resonance. Real application of NMR comes into picture only because of these internal interaction parameters. Continue further today. In that I am going to discuss today more about what is called chemical shifts. For example, consider a hypothetical molecule like this. I am showing you here a hypothetical molecule, and in the hypothetical molecule I have 3 functional groups which are put in 3 different colors: green, purple and blue. This is CH proton, NH2 and CH3. What is my resonance condition? Let us say I put this molecule in a magnetic field, strong external magnetic field, static field B naught. According to my resonance condition, nu is equal to gamma h into B naught over 2 pi. Gamma is constant for a given nucleus. Now I am looking at the proton NMR, that is hydrogen. So gamma is of proton I put. I say I fix this magnetic field constant. So B naught is constant. I know 2 is constant. I know pi is constant. So what do you understand from this equation? the resonating frequency for NH3 group, NH2 group, CH3 group and CH group, all the three will have the same resonating frequency, same frequency will be there if you calculate according to this equation. This equation does not distinguish resonating frequency for different functional groups. It only gives for a particular nuclei, for a particular gamma, what is the resonating frequency. As a consequence, for this an hypothetical case, if you consider for any molecule of your interest, if you take NMR should give only a single peak, nothing else. You cannot get anything more than a single peak. If this was the case, then what is the use of NMR? That is the question we have to ask. What is the use of NMR if you get only one peak for any molecule of your interest, and there is nothing wrong. This is 100% true because of this equation, resonance condition we have worked out. But what makes NMR very powerful is nuclear spin interactions, internal interaction within the molecule. That is what is going to make NMR a very, very powerful technique. What are these new internal interaction parameters? The nuclear spin is undergoing some interactions within the molecule. We will understand that, and that is what makes NMR very interesting. If I consider the nuclear spin interactions, I can classify this into two types. One is external interaction, other is internal interaction. The external interaction can be again two interactions. One is a Zeeman interaction, other is RF interaction. This we discussed extensively in the last couple of classes. What is a Zeeman interaction? You put the sample in an external magnetic field. I told you the nuclear magnetic moments interact with the external magnetic field. Remember, I calculated the energy E equal to minus mu into B naught, mu dot B naught. We calculated where I said magnetic moments interact with the external magnetic field. That is a condition to see NMR. Interaction of magnetic moments with an external magnetic field is a basic requirement. If mu is 0 because I is 0, then there is no NMR. That is what we discussed. So, one of the important interactions is Zeeman interaction. It is an external interaction, and nuclear spins are interacting with the external magnetic field that we discussed. Another is RF. We have to apply a radio frequency pulse in a direction perpendicular to the magnetic field to induce resonance. That is what we discussed, and I said bulk magnetization will be tilted to x axis or y axis by applying a RF pulse in a direction perpendicular to the bulk magnetization. It is an external interaction. You are applying from outside RF pulse, magnetic field is outside the molecule of your interest. So, these two are the external interactions which we already discussed, and from this we observed we are going to get only a single peak for any molecule of your interest by my previous slide, nu equal to gamma into B naught over 2 pi. So, this we discussed at strength, and we understood we get only one peak for any molecule. Now, what is important is internal interactions. We will look at the internal interactions. The internal interactions is another thing. We have 4 different categories. Within the molecule, internal means within the molecule I am talking. One is chemical shift, other is scalar coupling, third is dipolar coupling, fourth is quadrupolar coupling. Remember, this quadrupolar coupling is exhibited only by the nuclear spins which is whose spin is greater than half. The nuclear spins, the spin quantum number of this particular nuclei should be greater than half. Only such nuclei give rise to quadrupolar interaction. All other things, spin off nuclei will give this, then this. Quadrupolar coupling is only for spin greater than half. Now, the internal nuclear spin interaction can be further classified into 2 groups. One is a magnetic interaction, other is electric interaction. The magnetic interaction are 2 types, chemical shifts and spin-spin couplings. Electric interaction is quadrupolar spins only for spin greater than half. Remember, all interactions in NMR are magnetic except quadrupolar interaction for spin greater than half, that is an electric interaction. Understand the subtle difference. So, all interactions for spin half nuclei are magnetic. When you have a spin greater than half nuclei, you have quadrupolar interaction, that is electric interaction. Okay. Now, the chemical shifts is one of the internal interaction, magnetic interactions. I can classify it into two again. One is isotropic chemical shift, other is chemical shift anisotropy. This chemical shift anisotropy comes only in a system which is ordered or partially ordered or completely ordered. In isotropic chemical shift means in a regular solution state, where molecules are undergoing rapid tumbling motion, thermal agitation is going on, then you will not see that. Okay. Now, spin-spin coupling, again I can classify into two groups. One is a scalar coupling, other is a dipolar coupling. This now further, if I go take the spin half nuclei, for nuclei with spin greater than half, this is all are present, all the types of interactions are present now. I consider general example of any nuclei with spin greater than half, we have both magnetic interaction, electric interaction, chemical shift anisotropy, all those things are present. If I consider only spin half nuclei, that is what we are interested, we are going to discuss for the rest of the classes, rest of the course. We mostly concentrate on spin half nuclei. We are dealing with only magnetic interactions. So, we are dealing with only chemical shifts and spin-spin couplings. In the spin-spin chemical shifts, we deal with only isotropic chemical shift and CSA. If we are dealing with solids, we are dealing with scalar coupling, and if you are dealing with ordered system like partially or fully ordered system, we deal with dipolar couplings. For spin half nuclei, all these four interactions are present. But in this course, we are not discussing solid state NMR. Solid state studies was discussed in one of my previous courses in the advanced course. So, if you go to the solution state NMR, then what is going to happen is there is a motional averaging. Because of the motional averaging, this chemical shift anisotropy and the dipolar coupling both will get averaged out, it will not be present. What we are going to see is only isotropic chemical shift and scalar coupling. So, remember, we are going to deal with only solution state NMR for entire course. That means, we are always dealing with motional averaging. So, we do not have to worry about chemical shift anisotropy, we do not have to worry about dipolar couplings. All we have to worry about only two magnetic interactions, that is isotropic chemical shift and scalar couplings. These are the two parameters which we deal with in rest of this course. Because we are dealing with solution state NMR, motional averaging is there and all other anisotropic interactions are averaged out. Remember, every parameter in NMR is anisotropic, chemical shift is anisotropic, anisotropic part get averaged out, we get only isotropic. Coupling, scalar coupling, that is also anisotropic, anisotropic gets averaged out, we get only isotropic part. Dipolar coupling, anisotropic, quadrupolar coupling, anisotropic. Every interaction parameter in NMR is anisotropic. But when you are dealing with the solution state NMR, anisotropic component part will be averaged out and we are left with only isotropic chemical shift and isotropic scalar coupling also. Anisotropic part of this scalar coupling is averaged out. Okay. Now, we will all these internal interaction parameters we will start discussing. Of course, this we already discussed. One of the major external interaction is larger interaction is Zeeman interaction, because interaction of the magnetic moment with the external magnetic field B naught is the dominant interaction in NMR. For spin half nuclei, the dominant interaction is Zeeman interaction, where external interaction the magnetic moment of the nucleus will interact with the external magnetic field B naught. You may ask me, what is the interaction strength? Every interaction can be defined by its strength. What is the energy separation we calculated and we observed? Resonance in NMR appears in megahertz frequency range. That means the Zeeman interaction is of the order of megahertz. The strength of interaction is of the order of megahertz. That is the interaction strength. Please remember, Zeeman interaction strength is of the order of megahertz. Other sources of internal interaction for spin off nuclei, we have chemical shift, we have indirect scalar coupling or J coupling, and we have what is called the dipole coupling. Remember, chemical shift comes because of the charge distribution of the at the site of the nucleus due to electrons, surrounding electrons. There is a charge distribution that gives us to chemical shift. We understand more as we go further. We also get interaction of the one nuclear spin with other nuclear spin, where the polarization of the one nuclear spin is transmitted to other nuclear spin mediated through covalent bond, that is called scalar coupling, also called J coupling, also called indirect dipole coupling. There are several synonyms for it, but concept is same. Concept is interaction of the one nuclear spin with the other nuclear spin, where the polarization transfer takes place or the magnetization transfer takes place between two interacting spins through covalent bond. And the third one is a dipole-dipole interaction. It is the interaction between two nuclear spins, but there is no need of a covalent bond. It is a spatial interaction. Interaction can take place between two spins which are coming in space, close in space, coming close in space. It is like each spin is a tiny magnet. You can bring two magnets close to each other. Closer you bring it them, larger the interaction. Closer you bring it between them as close as possible. If the spatial distance is very close between them, then interaction strength is larger. This is a dipole-dipole interaction. And of course, I said for spin greater than half, we have quadrupolar interaction. These are the 4 interaction parameters. But for most of the cases, since we are dealing with isotropic solution state NMR, we have to deal with only chemical shifts and J coupling. That is all very worry. We do not need to worry about other parameters at all. In the entire course, we do not deal with other parameters. We deal with only chemical shift and J couplings. Of course, when we introduce NOE and that, we discuss about dipolar relaxation, etc. But we do not measure the dipolar coupling strengths. Now, if we come to the chemical shifts, how does they arise? Chemical shift is because of the electronic environment surrounding the nucleus, because of the circulating electrons surrounding the nucleus. As I said, the J coupling is interaction of one nuclear spin through other nuclear spin mediated through electrons, that is covalent bond mediated through chemical bonds. Now, other measurable parameters are this. It is a pairwise interaction, and this is a spin for quadrupolar spins. We will not worry about it. Now, we will start worrying more detail about how does chemical shift arise. What is the reason, how we can think of chemical shift? We all know the nucleus of an atom is surrounded by the cloud of electrons, okay? And it is like this. The external field induces the currents in the electron clouds in the molecule. You put this in the external magnetic field like this, the external magnetic field induces currents in the electron clouds, and this circulating molecular current in turn generates the magnetic field. Concept is simple, please understand. Put this molecule, any molecule of interest, in external magnetic field. The external field induces currents in the electron clouds, and the circulating molecular current in turn generates magnetic field. And as a consequence, what happens? Nuclear spins always see not only external magnetic field and the induced field because of the electrons. The nuclear spin sees the external magnetic field B naught plus the induced field. That is what we see. We do not see nuclear spins do not see only external magnetic field, and the induced field generated by the electrons always opposes the main magnetic field. Okay? It opposes the main magnetic field, and this is local field. Thus seen, the local field seen by the nucleus is not B naught by some additional factor coming because of the shielding electrons. This is called shielding constant sigma. So, B naught field gets reduced by this because of this. This is the local field. Local field seen by the nucleus is given by this condition. This is sigma is called shielding constant. Let us try to understand a bit more what is happening. Consider I have a nucleus, bare nucleus, no electrons surrounding it. Of course, hypothetical situation, you cannot think of that. Think of a situation, I have nucleus, knocked off all the electrons surrounding it. Then if you look at the charge distribution at the site of it, there is no charge distribution at all. This is how it is, bare electron, bare nucleus without electrons. Now consider a situation, I have a bare nucleus, put it in an electron cloud which is spherical in shape, spherical cloud of electrons, and this is the charge distribution. But this is a hypothetical situation. In reality, what is happening is you have chemical bonds. For example, consider the CH bond. Here, if I look at the proton or carbon either of the nucleus, at the site of this nucleus, the charge distribution is not spherical. The CH bond has a elliptical charge distribution. If you can see here, the charge distribution, unlike here, it is not spherical, it is elliptical. It is a symmetric ellipsoid. We call it as a 3-dimensional ellipsoid. It is like a ellipse. Okay. Go to OH bond. Here it is not even elliptical, it is a different shape, because oxygen is a electronegative atom, it withdraws electrons from the proton. Look at it, this is a different way, the charge distribution is slightly different, it is not same. Here it is different, see arrows are different here and here. Look at the arrows what I have written here, the thickness of the arrows here, they are all same, uniform, here also same, because it is symmetric. But once you come here, arrow thickness here is better compared to this, more thicker arrow here, charge distribution, because here it is more, I call this proton more de-shielded. Come to another bond like this, OH OC bond, here you see arrow thickness even more de-shielded here because of oxygen on either side. See at the site of each of these atoms you can calculate the charge distribution. What do you understand from this? Much larger electronegativity results in asymmetric clouds like this for this type of bonds. So, as the electronegativity becomes more and more, as the observing nucleus of your interest has surrounded by more number of different electronegative atoms, the charge distribution becomes more and more asymmetric, and it has a different funny shapes like this. So, the shielding at the particular site of the nucleus, shielding or de-shielding depends upon the surrounding atom, neighboring atom, whether it is electronegative or electropositive. Okay. Now, the question is, these atoms will induce the magnetic field. Okay, fine. What is the strength of the induced field? Okay, electrons induces the field at the site of the nucleus. But what is the strength of this induced field? Consider as an example, I am looking at a 400 megahertz NMR spectrometer. For this 400 megahertz for protons, I need a magnetic field of 9.3949 Tesla. 1 Tesla I told you is 10,000 Gauss. is 1 Tesla. So, now what is 9.3949 Tesla? If you express in gas, it is 93949 gas. The field induced now due to the electronic environment is this one. It is not huge number, 0.5093949, some number I have written, very small value. The field induced due to the electronic environment is much smaller. But what is the total field seen by the nucleus? It is this plus this 93949 gas plus the induced field, which is very small. So, it will become 93490009349, very small field induces, but that is effective, that is seen by the nucleus. So, the total magnetic field experienced by the nucleus is, in addition to the static magnetic field, very minute magnetic field induced at the site of the nucleus because of the internal interaction. Okay. So, what is the resonating frequency now? If I calculate the resonating frequency for this magnetic field, I said 400 megahertz, this is the magnetic field, this is the magnetic field, and this is gives 400 megahertz. But now I have added some number. So, resonating frequency is not 400 megahertz, and a small value which I have added here you can calculate by using nu equal to gamma into B naught over 2 pi. I have deliberately taken this number so that this will also become 400. So, it will become not 400 megahertz, 400 megahertz plus 400 hertz. What does it mean? The resonating frequency of protons is shifted by 400 hertz due to charge distribution. It is added 400, it is not 400 megahertz was here, but now there is another addition of 400 hertz. So, instead of coming here, it comes here. The resonating frequency is shifted by some amount due to charge distribution at the site of the nucleus. It is an internal interaction, and this is what is called chemical shift. The shift in the resonating frequency due to the chemical environment is called chemical shift. You understood how the resonating frequency is shifted because of the chemical shift. So, different functional groups in a molecule. Now, let us go back to the same original molecule. We have NH2, CH and CH3. What did we say earlier? When we did not consider the internal interactions, according to my equation, all were giving equal and give us to a single peak I said, because you got a gamma into B naught over 2 pi, all were same. Now, we have understood internal interactions. Charge distribution is coming because of the surrounding electrons. If you use that knowledge, now you see CH3 has 3 protons, the surrounding, there are 3 protons surrounding this, and the charge distribution at the site is much larger. Now, the shielding is bigger. I have deliberately put a bigger umbrella. Look at this one for NH 2 protons, I have put different umbrella here, size of the umbrella is different. Look at this, the size of the umbrella is even smaller. So, that means the shielding is different. The field induced at the 3 different sites are different, very small difference, but there is some significant difference. This may be 400 hertz, this may be 300 hertz, this may be 200 hertz, does not matter. So, the resonating frequency is not just 400 hertz, for this is 400 plus 400 megahertz plus 400, 400 megahertz plus 200, maybe this is 400 megahertz plus 100, we do not know. So, these are different. So, as a consequence, the resonating frequencies are different. This is more shielded, and compared to this we have different resonating frequencies. As a consequence, we do not get single frequency now, we are going to get 3 peaks, one for CH3, one for NH2, one for CH, and this is the beauty of NMR. Look at it, earlier I said we get only 1 peak, now we are getting 3 peaks, when we understood there are internal interactions for this. So, this is the important concept of chemical shift. Please remember this statement, nuclear spins do not get involved in the chemical reaction, but it gives information about the chemistry of the molecule, because we can understand what is happening at the site of the nucleus because of the chemical environment. Okay. So, this is what now the time is getting over. So, what I am going to do is I will stop here, but remember what we try to understand today. To summarize, today we understood there are different types of interactions. We classified into two types. One is external interaction, other is internal interaction. External interactions are nothing but Zeeman interaction and RF interactions, which we have been discussing since last 3-4 classes. Today we understood what is an internal interaction. Internal interaction is within the molecule, coming because of the interaction within the molecule, and there are 4 different types of interactions we understood: chemical shift, scalar coupling, dipolar coupling and quadrupolar coupling. If we are dealing with the spins greater than spin half, then quadrupolar coupling also will be there. But when we are dealing with spin half nuclei, we do not need quadrupolar interaction, that will not come into picture. But remember, these two interactions, all interactions are magnetic except quadrupolar interaction for spin greater than half, that is electric interaction. When we are dealing with spin half nuclei, only these 3 interactions are considered. Especially if you are dealing with the solids, dipolar coupling coming into picture, or partially ordered system, if you consider, dipolar coupling comes into the picture. But when you are dealing with spin half nucleus, especially in the solution state, the motional averaging removes dipolar coupling also, and all other anisotropic interactions like chemical shift anisotropy and J anisotropy, everything will go. Dipolar coupling will average out. We are dealing with only isotropic chemical shift and scalar coupling. These are the 2 parameters that are left with for us to understand. This and chemical shift, as I told you, comes because of the surrounding electrons. When you put it the molecule in a external magnetic field, the external magnetic field induces currents in the molecule. The circulating currents in turn generate magnetic field. This induced magnetic field opposes the main magnetic field. We have got a screening constant sigma s that we understood, and because of the internal interactions which are not identical for different types of bonds, CH bond has an elliptical charge distribution, OH bond is different, and different complicated bonds has a different type of charge distribution. As a consequence, in a given molecule, because of the neighboring atoms are having, whether it is a electron withdrawing or not, accordingly there is an effect on the particular nucleus, because the charge distribution overall, if you calculate how the charge is distributed, they may be different at different chemical sites. Because of this, when we went back to our original hypothetical molecule, we understood charge distribution is different for at the different sites of the same molecule. As a consequence, we have different resonating frequencies. So, the internal interactions gives us to different frequencies for different functional groups because of different induced fields, and this is what makes NMR very interesting. As I said, the nuclear spins do not get involved in the chemical reactions, but they give information about the chemistry of the molecules, because the charge distribution is getting reflected at the site of the nucleus by giving different resonating frequencies. We can understand what is happening at the site of the nucleus. This is what we understood about this thing. So, we will stop here, we will continue in the next class more about chemical shifts and try to understand what is happening for chemical shift in different molecules. So, I will stop here. Thank you very much.